Welcome to UVU CS3060 Lecture 9.8, where I give examples of memory management in various operating systems and architectures. We'll start with the Oracle SPARC Solaris system. The Solaris operating system is a modern 64-bit operating system that is tightly integrated with the hardware, meaning that the hardware is specifically addressed and it is not generic as is with other operating systems. We're looking to be as efficient as possible in this with low overhead. The Solaris operating system uses a paging system based on hashing, but is slightly more complex. It uses two hash tables. There is one hash table for the kernel and one hash table for all the user processes. So we have kind of an inverted page table system where we're using hashing instead of just simply doing a direct lookup. Each of these entries, each of the maps, so with these two hash tables, one's for the kernel, one's for all the user processes, each of these tables map main memory or the logical memory addresses from virtual to physical memory. The way they do this is they represent, each entry represents a contiguous area of mapped virtual memory, meaning that several pages are represented with a particular entry. This is more efficient than having separate hash table entries for each page. It actually allows us to have a hash table entry spanning several pages of virtual memory. Each entry of the hash table has a base address, so where the particular frame starts, and the number of pages, or the span, the number of pages that that particular entry represents. So you might have 1,000 pages represented to one hash entry. So basically it is making larger partitions of smaller partitions. The TLB holds translation table entries for fast hardware lookup. So basically this is a cache of TTEs that is in a translation storage buffer. And so there are entries for recently accessed pages within this translation storage buffer. A virtual address causes a TLB search. If there's a miss, then the hardware will walk the TSB looking for this translation table entry to see if it finds a match. If a match is found, then the CPU copies the TSB entry into the TLB entry. If no match is found in the TSB, the kernel is interrupted to search the hash table, which then creates the TTE and stores it in the TSB, and then returns control back to the memory management unit, which completes the address translation. So this is a very interesting system in that a memory access may cause the instruction to be interrupted by the operating system, where the operating system goes through and manages all of these buffers so that it can return control back to that instruction that attempted the memory access. This can really slow things down if not done properly, but clearly this is an efficient method for the SPARC Solaris system. Now, with Intel, we have two different architectures, a 32-bit and a 64-bit architecture. Clearly, Intel is the dominant chipset, although ARM would like to take its place as quickly as possible. And there are other good systems. In the Pentium CPUs, a 32-bit architecture is prominent, and those are normally called IA, Intel Architecture 32. Current Intel CPUs are IA64 architecture, and there are all sorts of variants on this. So, traditionally, when it comes to the Intel IA32 architecture, there is support for both segmentation as well as segmentation with paging. The original segmentation comes from basically before the Pentium days and is legacy architecture implementation, but it's still there and you can still implement it. You can have up to 16,000 segments per process. And in segmentation, we divide things up into two partitions. The first partition of up to 8K segments are private to the process. We call this the local descriptor table. And the second partition of up to 8K segments is called the global descriptor table. So the CPU will generate logical addresses as typical, but what happens is this, there is a selector which tells us which segmentation unit to use. The global identifier determining which particular table to use, whether it's the global or the local. And what will happen is this will generate the physical address that will find out from get the segment where the frame is, and then be able to find the proper page. Now we have here the page size, which can be 4K or 4 megabytes. So logical to physical address translation. First, the logical address goes through the segmentation unit. That provides a linear address, which goes to the paging unit. The paging unit looks up that particular address within a page number and finds the physical address. So you can see here that we have our offset and we have our selector. The selector decides which descriptor table to go to, finds the segment descriptor, and then adds the segment descriptor and creates the 32-bit linear address. In 32-bit paging systems, we have our 12 bits of offset, which define a 4K page. We have our first page table, which identifies the inner page table, and we have the upper 10 bits here, which identifies the page directory. The page directory is actually, the location of the page directory is stored within what is called the CR3 register. This is a protected register that can only be modified in kernel mode that points to the page table. Each address is looked up in that page table based on the upper 10 bits. The middle 10 bits gives us the inner page table, which gives us access to our 4K page. We also have 4 megabyte pages. In a 4 megabyte page scheme, we have 22 bits of offset, and that 22 bits of offset has a one page table level, just simply the inner page table, or the outer page table, in which case it looks up in a 4 megabyte page. Remember that we want to be careful using the proper page size so that we do not experience fragmentation in order just simply to eliminate a level of page tables. We also have what is called page address extensions. There was a problem with the physical addresses where the memory it could not be accessed beyond 4 gigabytes. And so in order to address beyond 4 gigabytes, this page address extension was introduced, which basically gave us a 3-level scheme. It takes the 10 bits, or it takes the 12 bits for offset. It takes 9 bits for one page table. It takes another 8 bits actually. 9 bits for the second page table. And then it uses 4 bits for a page table directory. So we have 3 layers here. In effect, what this allows us to do is it increases our address space to 36 bits. The upshot here is we're allowed to change our page directory and page table entries to 64 bits in size, meaning that these particular entries are actually going to be slightly small. There's going to be less entries, but they're going to be bigger in size. So instead of having 4 bytes per entry, there will be 8 bytes per entry. Thus, our page table size goes down from 10 to 9. So we have 512 entries here, 512 entries here, and then 4 entries here in our outer page table. We actually get to increase our address space to 36 bits, which is 64 bits of physical memory. 64 gigabytes of physical memory, as opposed to 4 gigabytes of memory. Frankly, this was a hack in order to get more physical memory access. There was a better solution in the long run. And that solution is the Intel 64-bit memory access. 64 bits allows you to access 16 exabytes of memory. So if you have a logical address space of 16 exabytes, I don't know of any machine that has exabytes of memory. We have terabytes. Petabyte machines do exist, but they're rare. Exabytes, I do not think there is one at this point. Doesn't mean it won't happen. In practice, we don't use all 64 bits for the logical address. We only use 48 bits for the logical address. But even still, 48 bits is giving us terabytes of memory. In fact, this 48-bit addressing gives us, I'm just trying to think here, 128. So we have quite a bit, 128 terabytes of memory. We can have varying page sizes. We can have page sizes of 1 gigabyte, or 2 megabytes, or 4 kilobytes. Now we have 4 levels of paging hierarchy. Remember that each entry now takes up 8 bytes, and so we can only have 9 page table entries. So in this particular case, we have our 12 bits for 4K page. Then we have a page table entry of 9 bits, another page table entry of 9 bits, another page table entry of 9 bits, and finally a 4th level of 9 bits. This gives us 9 times 4, 36 bits of page table entry, plus our 12, which are used to address 48 bits of logical memory. Each page table entry can actually point to an entry, or this final page table that points to a 52-bit entry, which takes us beyond the petabyte and actually gets us it takes us beyond terabyte and gets us into the petabyte range. So petabytes of RAM can be accessed there, whereas 48 bits just simply does terabytes, 128 terabytes. So when we have petabytes of physical memory that can be addressed and processes that can allocate terabytes of memory, we are clearly looking to expand to just fantastic amounts of memory. But consider how many memory accesses we have with the TLB MIS. We have 1 here, 1 for the for the first level, 2 for the page directory, 3 for the second page directory, 4 for the page table, and 5 for the actual memory access. So clearly a TLB becomes very valuable at this point in eliminating all these page table accesses. So when it comes to the ARM architecture, The ARM architecture is generally a 32-bit, although there are 64-bit ARM systems at this point. In the ARM architecture, there is either 4 kilobyte or 16 kilobyte pages. These pages are divided up into what are called sections of 1 megabyte or 16 megabytes. If you're using sections, sections have one level of paging. If you're using pages, you actually have 2 levels. So there's 2 levels of TLBs in this particular case. The outer level has 2 micro TLBs that are used for data and also for instruction. And then you have the single main TLB that is that is used by the CPU. First, the inner TLB is checked. On a miss, the outer is checked. On a miss, the page table walk is performed by the CPU. This brings us to an end of lecture 9.8, where we give memory management examples in various architectures.